So there are three properties that we need to remember for this. Our product property is when we have like our base raised to the m power times our base raised to the n power, we can just add the exponents there. All right. So there's a couple examples here. If you have x to the fifth times x to the third, you're just going to get x to the 5 plus 3, which will give you 8. Or if you have 2 to the x times 2 to the third, that is 2 to the x plus 3. So those are examples of the product property. If you have two bases multiplied together, you can add the exponents. We also have the power property, which says that we're taking a power and raising it up to another power. In that case, you're going to multiply your exponents. And if you need justification for this, you can think about x to the fifth times x to the third. That is x times x times x times x times x. There's 5 x's times x times x times x, right? There's 8 altogether. So if you're doing x to the fifth 3 times, that's x to the fifth times x to the fifth times x to the fifth. And so you would add those 3 together, 5 plus 5 plus 5, you would get 15 in that case. So powers to powers, you multiply. This you're going to add. And then negative exponents. I think I was talking about negative exponents being the bad children the other day. Did I say that in here, or was that the other class? So you send them to the basement. That fixes the problem, makes their exponent positive, right? So those are the 3 things that we are going to need to be able to sort of rewrite exponentials today. One of the things we're going to look at is changing horizontal transformations into vertical transformations. So if we look at like example A right here, currently we would be looking at the graph of f of x equals 4 to the x, and there's a little plus 2 up there in the exponent. What is that plus 2 going to do to the graph of 4 to the x power? It's going to move that graph to the left too, right? Because in an exponential, there are not parentheses, but whatever is in your exponent, you can think about it as having parentheses around it, right? So currently, this is f of x. Well, let's not call it f of x. Let's call it y equals 4 to the x shifted left 2. Okay? For this. But we can have sort of like equivalent transformations here. Whenever I have 4 to the x plus 2, I could break it back apart, right? I could write this differently. So if I take f of x equals 4 to the x plus 2, I could write that as 4 to the x times 4 to the second power. Is everybody okay there? We're just taking that product rule, product property, and we're going backwards. Instead of saying that we've got x to the fifth times x to the third, we're saying, oh, I've got x to the eighth, let me break that back apart into x to the fifth times x to the third, right? So since I got these two things added, I'm just breaking that back apart. Now, 4 to the x has to stay like it is, but what is 4 squared? 16, right? So now I've got 4 to the x times 16. And if I want, and I do, I could rewrite that as 16 times 4 to the x. Have I gone ahead of myself? I've gone way ahead of where I'm supposed to be going because I did not read the directions carefully enough. The directions say, determine the horizontal transformations of each of the following exponential functions. They did not ask us to go vertical yet, did they? No. I was really supposed to stop right here for that. But since I went too far, what are we ending up with down here at the end? It's not a shift left or right anymore. What's this 16 do to the graph of 4 to the x? Vertical stretch. So now we would have like y equals 4 to the x, or stretched, or I could say dilated vertically by 16. I'm getting ahead of myself, though. I wasn't supposed to do that on this problem. I was really just supposed to talk about the shift. Look at the next three there and just tell me about what type of shift. So like for B, the original function here would be y equals just 2 to the x power. Right? So exponentials are a little tricky because your base is a number, but that number is not part of your like transformations that are happening. Like this right here, your 9, your y equals 9 to the x would be your parent function. So tell me about those transformations there. All right. I think D is the easiest because I think like translations are easier. So this will be y equals 5 to the x power. And Braden, what has happened to that y equals 5 to the x power? Very good. Right 1. Because you would have little parentheses around that x minus 1. And so whenever you have something inside of the parentheses, or in this case inside of the exponent, then that's going to be a shift left or right in the opposite direction for that. Okay. I think these two are trickier. I think B's a little tricky. I think C is the trickiest of these here. So for these, we are not adding or subtracting, so we're looking at a dilation, right? We're looking at some sort of dilation. Who can tell me what they think happens on B? Destiny, what do you think happens on B there? Perfect. Y equals 2 to the x is dilated horizontally by factor of 1/3 there. So again, inside of the parentheses, remember everything's backwards. So if you're multiplying by a big number, 3, then you're going to be flipping that and making it 1/3 for your factor there. So this is going to be a horizontal compression. It's going to get squished in this way. Okay, what about C? For C, we are dividing by 2. And I don't really have any rules where I divide. Everything's either multiplying or adding or subtracting. All right, so what is happening for C? Any ideas? Anybody think they know? Correct. Perfect. So instead of thinking about like dividing by 2 right there, we can think about this being 9 to the 1/2 times x, right? That would be the same. If you multiply something by 1/2, that's the same as dividing by 2. So this is y equals 9 to the x power dilated horizontally by a factor of, the 1/2 has to get flipped here. It's going to be 2/1, which is, of course, just 2. So that's just a review on transformations, right? So we were supposed to be just reviewing. I went way too far on A. So our next step is to see if we can make an equivalent transformation. And I've basically already gone through that, which he goes through here. and we have a vertical dilation by a factor of 16 for that first one there, because I didn't read my directions as well. So every horizontal translation of an exponential function is equivalent to a vertical dilation of the exponential function here. So each of the following exponential functions has a horizontal translation. For each, write an equivalent representation that has a vertical dilation and no horizontal translations. Let me back up just a second. I think it's helpful. These will be calculator inactive, but I think it's helpful to see what this is even talking about here by graphing this on Desmo. So if we go back to that A, if I have f of x, I'm going to put f of x equals 4 to the x power. That would be the parent function that we're dealing with right there. Whenever I do y equals 4 to the x plus 2, we can see that graph right there has just been shifted to the left some. But if I do y equals, I'm going to do this, a times 4 to the x power, a times 4 to the x power, and I'm going to put a slider for my a. This is a vertical dilation. That means we're stretching that graph up taller and skinnier. Notice as I change that, that green line gets closer and closer to the blue line. I'm going to have to change this up here where this goes up higher. And if I get right there at 16, it's exactly the same, right? I think, especially with exponentials, vertical stretches are really hard to see what's happening there because this graph already shoots up so quickly, right? So seeing it be taller and skinnier is really hard to deal with visually. That's why it's really important that we know our rules for how to look at the equation for those. All right, so if we've got f of x equals 2 to the x plus 3. Currently, Asher, we have y equals 2 to the x, and what type of transformation do we have? Left 3. Perfect. So that graph is just y equals 2 to the x shifted to the left 3, as it is right now. But they have asked us to write in terms of a vertical dilation with no horizontal translation. So that means we've got to rewrite this. So we're going to do like we did on the problem that I went too far on. I have addition right here, so I could rewrite this as 2 to the x times 2 to the third. 2 to the x, I've got to leave it alone. I am going to put it over here on the back side just because I want it to be in the a times b to the x power form. What is 2 to the third? 8. So that's going to go right here. And now f of x is still the same function, right? It looks a lot different, but it gives all the same values as the original function. If you're not going to be able to use Desmos on a lot of these, but if you just want to check yourself on these when you're working on homework or something, you can just go in here to the x plus 3 and type in f of x equals 8 times 2 to the x, and you can see those are the same graph. Oh, gosh. Those are the same graph right there. So you know that you have done it right. If you mess it up, then you won't get the same graph for those. This is going to be a vertical dilation by a factor of 8. For that vertical dilations, we just use that factor that's there. You don't have to flip anything. Okay, try these next two on your own. Most of you are breaking this up into 3 to the x times 3 to the negative 2. which is what you need to do right here. And then dealing with that 3 to the negative 2 is where we were having trouble. So negative exponents are like bad children. And what do we do with our bad children? We send them to the basement, right? So that 3 over 3 to the negative 2 is all in the numerator right now. Like if there were a denominator, there's nothing there, right? So you take the 3 to the second and you put it in the bottom. Now I did move this up to be like the first term because I know the 3 to the x needs to be at the back. There. So that goes here. And then 3 squared is 9. So you get 1 over 9. I saw a lot of negative 9s whenever I walked around. But one thing to remember, if your number you're raising, think about this. If you're raising any number, if you're raising any number b to a negative power, negative 6, if b is positive, can the result be negative? Can you ever raise something to a negative power and it will give you a negative number if you didn't already start with a negative number? Never. Because all negative exponents do is send things to the basement, right? They do not change the sign of the number. Now, if b is already a negative number, if you have like negative 2 to the negative third, you might end up with a negative answer. But if this is a positive number here, then you're still going to have a positive number whenever you get done, which seems wrong because we think of, when we see that negative, it feels like there should be a negative answer to it, but there is not. So raising something to a negative power, it's going to stay positive. It'll just be like a fraction there. So this is going to be a vertical dilation by a factor of 1/9. And since that 1/9 is a small number, that means you're taking this vertically and squishing it in. Okay. C is a little tricky because it's got the 4 out front. So what you're going to do with that 4 is you're just going to leave it alone. It's just going to stay out there out front. The x plus 2 only goes with the 3 because there's not like an extra set of parentheses that includes that 4. So this x plus 2 only goes with the 3. So you break this up into 4 times 3 to the x times 3 to the second. And then I took that 3 to the second and put it right here, made it 9. I put the 3 to the x at the end, and that 4 just sort of hangs out front. So then you're thinking about what you can combine. You cannot combine anything with this 3 to the x power because that 3 is being raised to the x power. It makes it like a separate term, a different term. Just like if we are like adding like terms and we've got 2x and 2x squared. We can't add those together, right? So when we have an exponent right here, we have to leave that alone. But 4 and 9 can be multiplied together, which will give you 36 right here. So another thing that might be tricky about this, I did not put the final answer here because I think there's a couple ways they might give this to you. For these, I should have said this is y equals 2 to the x is being dilated vertically by a factor of 8. And here, this is y equals 3 to the x. So if we're just doing y equals 3 to the x, that is a vertical dilation by a factor of 36. If this is a multiple choice problem, there is also a possibility that they could think of it really like this we had before. Think of it as maybe like 9 times 4. Actually, no. They're not going to do that. They're going to do it the way I've got it here. You're good. They won't try to do k to the x. Mm-hmm.
So it's kind of like just take out the x exponent and just solve the problem.
Yes. Okay, we okay here? So, every horizontal translation, it could, whether it's a shift left or right, or an expansion or compression, is, actually no, any shift left or right is going to have a vertical dilation that goes with it. Okay? Now, let's think about what happens like in the power property. Okay? So, if we have a power property, which is a horizontal dilation, that can be rewritten as a vertical, well, actually, I think it changes the base is what happens. Let me remind myself. Yeah, it changes the base. So, in this case, I've got, we're supposed to decide which one of these is equivalent. I've got y equals 9 to the 2x. Now, this is 2 times x. It is not 2 plus x in this case. So, currently, this is a horizontal dilation by what factor? 1/2 for that, because it's inside of the parentheses, so it's backwards, right? So we have a horizontal dilation by a factor of 1/2. So I want to rewrite here, and to do that, I would have to use the power to a power property. We're not adding here, so this is not going to be 9 to the second times 9 to the x. That would be incorrect. There. All right. For things that are multiplied together, we're going to have y equals, we can write it either way. We can write it as 9 to the second to the x power, or you could do 9 to the x to the second power. However, this one is going to be more useful here. And what is 9 to the second? 81 to the x power. So that is going to have a different base, right? Another option on a problem like this is that if you forgot how to do it, now the numbers get a little bit large, plug in some numbers and see what works, right? So zeros, well, 0 will rule out 1. Like if I do 9 to the 2 times 0, that is just 9 to the 0, which is 1. Well, if I plug in 0 here, I'll also get 1. And if I plug in 0 here, I'll also get 1. If I plug in 0 in the bottom one, I'll also get 1. But 3 times 9 to the 0 would be 3 times 1, which is 3. So you could rule out B, right? Then I could do 9 times 2 to the first power, which is going to be 9 squared, which is going to be 81. And so if you plug in 1 here, you're just going to, not 3 to the first is just going to give you 3. Can't be that problem. We already ruled out B. 18 to the first power is going to give you 18. I'm going to rule out that one, but 81 to the first power is going to be 81. So that'll work for those. So if you're, I want you to be able to do it with like the manipulation of the function, but if you're stuck on the multiple choice question, remember that's always sort of an option for you. Okay, let's keep going. Here, last one. Which of the following functions is an equivalent form of the function 9 times 4 to the x power? And then I'm looking at all of my options. And I've got 3 times 16 to the x over 2, 3 times 16 to 2x. So notice all the bases right here have turned to a 16. Correct? So here, I need to know which one can match this. Now, I have the option of plugging in some numbers, right? I could be like, oh, 9 times 4 to the 0, and I could plug in some numbers. And then I could do 9 times 4 to the first power and plug in some numbers and see what works. And if that doesn't do enough, 9 times 4 to the second power and see which one works. It's not the fastest way to solve the problem, though. In this case, if I've got 16 to the x over 2, that's the same as having 3 times 16 to the 1/2 x, right? Dividing by 2 is the same as multiplying by 1/2. We saw that on another problem, which means I would have 3 times 16 to the 1/2 raised to the x there. Oh, fractional exponents might be something we need to take a minute on. Does anybody know what 16 to the 1/2 power is going to be? It is 4. Because raising something to the 1/2 power, what's that the same as? A square root, right? So this is going to be 3 times 4 to the x power. Is that equivalent to what we started with? Close, but not, because that 3 doesn't need to be adjusted. So which answer choice is going to be correct? C. Right there. For fractional exponents, if we need a reminder here, I'm not sure to what extent you guys worked on this. If you have, let's just make ourselves fractional exponents. So if you have x to the a over b, that is going to equal the b root of x to the a power. So like in this case, we had 16 to the 1/2 power. The number on the bottom of the fraction is your root, right? Roots are on the bottom of a tree. So the root that goes out here is the bottom of the fraction. So that would be the square root. We don't normally write the 2 on a square root, but we could, right? A square root of 16 to the first power, which is just the square root of 16, which is 4. That's what we're doing here, right? But you could have different options. Like, for example, if I have 8 to the 2/3, right? What type of root am I going to have? Cube root of 8 squared, right there. I could square the 8, could get 64. Or you can think of it this way. You can write it this way, or you can do cube root of 8 squared like that. Because as fractional exponents, we could switch them there. And what is the cube root of 8? 2. So we're looking at 2 squared, which is 4. So some of the problems you're going to do are you're going to run into some of these fractional exponents right here, and this is going to be something that you have to work with. Everybody good here? For that second example, I mean the cube root of 8. Square the 8 first, yes, and you have 64. Sometimes that is, like, in this case, it's pretty much fine to do that because 64 is not a huge number. Like, if this was the 7/3 or something, then we would have 8 to the 7th there in the middle. And you could find 8 times 8 times 8 times 8 times 8 times 8 times 8, maybe. But then if you get that, you're not going to know what the root of that is because it's going to be such a huge number that it's going to be hard to find. So I like to find the root of like the smallest number possible a lot of times for those. But it would be fine to do cube root of 64. You'll get the same answer there. Okay, everybody feel okay? All right, we are going to